before I start, if you have any queries from the previous class, then we can discuss that. Any questions?
No, ma'am.
Okay, in that case, let us get started. So you can see my slides.
Yes, ma'am.
Yes, ma'am. Yes, ma'am.
So today now we have looked at RNN and LSTM, etc. So we discussed that RNN, there are different types of models depending on whether you have a sequence in the input or sequence in the output, etc. So it can be as many to one, one to many, many to many, etc. So today we will look at a specific type of RNN architecture called the encoder-decoder model, where there is a sequence in the input and sequence in the output. And as an example, let us consider the task of machine translation, where you are given a sentence in one language. Let us say you are given a sentence in English containing these three words, and you want to translate it to Hindi, right? So the input is a sentence, which is a sequence. The output is another sequence. But these two sequences are not necessarily aligned. And the length of the English sentence and the length of the Hindi sentence may be different. So what the encoder-decoder model does is that it first takes the sequence, the input sequence, and then after it has completed looking at the input sequence, it then starts generating the output. Okay. So after doing, so these are the hidden nodes at the input. So the hidden node at this point, this is used as an input to the decoder. So this part is called the encoder and this part is called the decoder. So decoder takes this as the input. So this state captures the essence of the entire input. This is taken as input to the decoder and the decoder starts generating the words in the target language. Suppose this is the first word which is generated. The next word will be generated based on this hidden state, and this previous word may also be given as the input. Okay. So this is the basic model of neural machine translation or encoder-decoder, which has various uses. And in general, this type of architecture is useful for what we call a conditional language model, where the output is conditioned on the input sequence, or we can say generation with a prefix. So there is an initial sequence which is given as input. Conditioned on that, the subsequent outputs are generated. Is this clear? Any questions? Do you have any questions on this picture?
Ma'am, can you repeat this slide once again, please?
Any questions? I cannot hear you.
Hello, ma'am. Ma'am.
Hello?
Hello, ma'am. Can you repeat this slide once again?
I think somebody is speaking, but I cannot hear. Can you hear me?
Ma'am, he's saying that if you can repeat the slide once again.
I'm sorry, I cannot hear you. You can put it in the chat box.
Ma'am, he's asking that if the slide can be repeated.
As I said, I cannot hear you.
Ma'am, we can hear everybody.
Either you can be loud or put it in the chat box.
I think the problem is in your end.
Can you see my slides?
Yes, ma'am, it is visible. Hello, ma'am.
Ma'am is saying to repeat the slide. Which slide? The previous slide. Can somebody speak up who I can hear?
I think the problem is at your end. We can hear everybody's voice.
Hello, ma'am. Can you hear me?
It's very faint with,
Ma'am,
don't
we
know.
can hear you perfectly.
I don't know why I cannot hear you. Right.
Ma'am.
So if you have a question,
ma'am.
please put it in the chat box. Somebody says repeat the slide, this slide. So the slide is there. If you have any questions, let me know. Is the slide clear to you? From beginning you repeat. I can repeat, but if you have any question, please ask. Just repeating will not help. You can play the slides. If you have any question, please ask. Anyway, I'm explaining the slide again, but please pay attention, ask specific questions. Otherwise, I cannot proceed with this class. So we have a model called the encoder-decoder model, where there is the encoder. The encoder takes a sequence as input, okay? And this is an RNN which is taking the sequence as input. This is the hidden layer. And at the end of the sequence, the state captures the information about the entire sequence, which is fed to the decoder part of the RNN. Is this clear? So Shivam says, I think the problem is at your end. So what is the problem? You cannot hear me?
Hello, ma'am. Now,
Yes.
are we on? Okay. Yes, ma'am. Now it's fine.
I'm sorry, I cannot hear you. I don't know why. Okay, please put your questions on the chat since I cannot hear you.
Hello, ma'am.
So can somebody else speak out? Saurabh Bhattacharya, are you there?
Yes, ma'am. I am here. Hello, ma'am. Am I audible?
I can hear you, but not very clearly. Okay, let me proceed. So put your questions on the chat. So in the decoder, it accepts, the input, the previous input, as well as the previous hidden state, and it generates the output. So the output is one of the words in the target language, and therefore you generate a probability distribution on all the words, and from that the output is generated. Okay. So conditional language model can also be used for other tasks. For example, from a picture, you want to generate the textual description. And in that case, the encoder may be even a CNN. The CNN takes the picture and comes up with a vector which represents the picture. And from that, you can have the decoder which generates a description of this picture. So this is in general a sequence to sequence model where you have an encoder. Encoder can be an RNN or could be a LSTM, CNN, etc. And you have an RNN or LSTM based decoder. Okay. So typically, there are two separate RNNs, one for the encoder, one for the decoder. So you have parameters for input to the encoder and hidden state of encoder to the next hidden state of that encoder. So there is one set of parameters here. And then you have parameters for the decoder state. So these parameters, so these are suppose W1, these are the parameters W2, these are the parameters W3, these are the parameters W4, and these are the parameters W5. Okay. So these are the parameters corresponding to this encoder-decoder model. And you would also feed in this input, this output to the next input. Or, while training, you can feed the previous output to this input. Now, this type of encoder-decoder model also can have multiple layers. For example, this shows an encoder-decoder with 3 layers. And there are various cases apart from machine translation or caption generation where encoder-decoder model is used. For example, text summarization, where the input is a text and output is a sentence, which is output is another text which is shorter, which is a summary. You can also use this for question answering, where the input is a question and the output is the answer to the question. It can be used for code generation, where the input is a text and output is a code, and so on. Now, you can also, have for the encoder-decoder, because if you have this sort of model, what happens is that the last state captures the information about the entire sequence, and some information from the previous thing may be lost. Of course, you can use an LSTM, but often you can use a bidirectional RNN or a bidirectional LSTM, right? Where you have one at each layer, you have one RNN going from left to right, another RNN going from right to left, and you concatenate the 2 hidden states to give the context. So in an encoder-decoder network, an encoder accepts an input sequence and it generates a corresponding sequence of contextualized representation. And from the encoder, you get a vector called the context vector. And this context vector is taken as input by the decoder. And the decoder generates the output. And the output generation is autoregressive. First, the first element in the sequence is generated. From the first element and the previous state of the decoder, the second element is generated, and so on. Yeah. So typically, this is how it happens. The context vector, in the simplest case, is the last hidden state of the encoder. So this is the HN of the encoder. This is H1, H2, HN. So this last hidden state of the encoder is taken to be the context vector. And the context vector acts as the 0th state of the decoder. So this is H0 of the decoder, which feeds into H1 of the decoder, H2 of the decoder, and so on. Now, in the decoder, HTD, the Tth element of the hidden state of the decoder, is some function of the previous output generated, which is y hat t minus 1, and the previous state of the decoder. So this is taken as the input and this. So these two are the input to a decoder state. And from the decoder state, if you want to generate the output, there is a function of HTD gives you ZT. And from ZT, because the output for a machine translation is a word, and as you know, for classification, you can use a softmax function. So on ZT, the softmax function is used to find the probability distribution of the different words in the target language. So there are some questions. Shomode, after getting the first output, for the next output, do we need to pass the previous words or just the previous predicted word? So in this architecture, the previous predicted word is given. For example, for the hidden state T, y hat t minus 1 is input. Okay. And ht minus d captures what is there in the previous output and the input. Right? In an RNN, the current hidden state captures the essence of the previous states. Right? And the output, only the previous output is fed. So Vaibhav is asking what is the importance of giving hidden state and output as the input to a next layer? How it will be different from our previous method? I do not know what is the previous method. I mean, this is the method that we are talking about in the encoder decoder. Of course, the hidden state, the previous hidden state is supposed to capture all information of everything so far. In addition, we give the previous output in order to get the next output, because in a language model, in a sequence, the previous output has a role to play. Okay. So the next word also depends on the exact word which was output. Of course, it depends on all the words which were output, but the immediate previous word is given as the input. So Vaibhav, does that answer your question? Vaibhav, can you say yes or no?
Yes, ma'am.
So for encoder, you can use, if you have a sequence, then you can use RNN, LSTM, GRU, etc. For example, you can use multi-layer RNN, multi-layer LSTM, bidirectional, etc. So bi-LSTM stands for bidirectional LSTM. If your input is an image, you can even use a CNN. So the decoder is said to be an autoregressive generator, where YT is output depending on Y hat T minus 1 as well as the previous hidden state, and the decoding goes on until a special symbol called end of sentence is generated in the case of machine translation, because there is no fixed length of the sentence. Okay. Now, there are certain weaknesses of this system that we described. The context vector that we get is the last hidden state of the encoder. And this is a vector of fixed size. And this is the only input that the decoder gets. Right? The decoder gets only the context vector as the input. And the context vector, as we have described, is the last hidden state of the encoder. Now, this creates a bottleneck because this context vector is a fixed length vector. And if the input sentence is very large, all the information has to be contained in this. Also, if you have a long sentence, the influence of the previous words, they become less and less important as the output sequence was generated. As we discussed, if you use an LSTM, LSTM helps us carry forward information without forgetting. But if the information of a long sentence has to be preserved, even then, this context vector acts as a bottleneck. So the solution, one solution to it, simple solution, is to make this context, at least make it available at each step in the decoding process. So in our first model, the context vector was fed to the first state of the decoder. Right? The context vector was fed to the first state of the decoder. Now, just to, a simple improvement is to feed the context vector at all decoder states. The same context vector at all the decoder states. So, in the decoder state, HTD, the TF decoder state, is a function of T minus 1th decoder state, the previous output Y hat T minus 1 and C. So the context vector is taken as input at every decoder state. Okay. Now, so the next we will look at how the output is generated. Now we said that, we will have this Tth decoder state, and from that we will compute Zt, and from that Yt. And Yt, we said that we will get from Zt, we will get, using softmax, we will get a probability distribution. Now, from this probability distribution, you have to choose the word which is going to be output. Now, how are you going to choose the word depends on your task. So in general, if you want to have diversity in the output, you can sample a word according to the probability distribution that you have obtained. But in the case of machine translation, sampling, we may give you, some wrong sequences. So in machine translation, you are looking for a specific output sequence, and you can think of, different options. The simplest option is to take the word which has highest probability. Okay? From this probability distribution, so suppose, these are the probability distribution that you have got in the output. You find out the word which has the highest probability, and that word is output. So this is called greedy decoding. In greedy decoding, in general, in the decoder, at each state you generate the probability distribution on all words in the target language. And in greedy decoding, you pick the word with the highest probability. So Vinod has a question. When we use this for image captioning application, how do we establish the association between different classes so that the semantics of the image is extracted? So I'm not sure I understand what you mean by how establishing the association between different classes. What classes are you talking about? So the second part of the question is, how is the semantics of the image preserved? So if you have a CNN, a good CNN architecture like ResNet or InceptionNet, etc. So at the end of this architecture, you get a representation of image, which you hope can capture a lot of information about the semantics of the image. Does that answer your question, Vinod? Can you speak up? Vinod?
Ma'am, am I audible?
Is this okay?
Ma'am, am I audible?
Now, this greedy decoding is sometimes, it is not very appropriate, because it may lead, the locally greedy solution may not give you the best output for translation. So an alternative to the greedy decoding is a method called beam search. In beam search, what we do is that after we feed the sequence, here we just have noted that in sometimes for machine translation problem, it works better if the input sentence is fed in reverse. Okay, if you're not using bidirectional RNN, feeding the input sentence in reverse works well, and this problem can be circumvented by using a bidirectional RNN. Okay. So anyway, what we really want to tell is that in beam search decoding, from the probability distribution that you get, instead of taking the word with the highest probability, you have a beam size, which is, let us say, 2 or 5 or 10. Suppose beam size is K, then here you choose the 5 words with the highest probability, the 5 most probable words, or K most probable words. At each step, you choose the K most probable words, and you use a non-greedy method, which finds out a sequence based on certain constraints, whose probability is the highest instead of taking a greedy decision. So I will illustrate it subsequently. For example, suppose this is French sentence is input or French phrase is input, unshort minon. I'm not pronouncing it correctly. So we feed this in reverse, and suppose at the output in the first state, there are two possibilities, a and 1, right? 1 has the higher probability. However, if you choose 1, so suppose the best translation for this sentence is a cute puppy. So a is more appropriate, but locally 1 is the higher probability. 1 has a probability of 0.51, A has a probability of 0.48. At the next state, we have two outputs, puppy and cute. So puppy has 0.47, cute has 0.53. And in the third state, the outputs are puppy is, etc. So there are multiple outputs that you consider at this state. And from this multiple outputs, you are going to choose one word at each stage so that the overall probability is maximum. So you want to find out the probability of a sequence at the output given the input, which you can compute by, this is the standard chain rule of probabilities. You look at probability of yi at the tth step conditioned on the input and the output so far, and you take the product of that. Now, so if there are k outputs at every state and suppose the sequence is of length t, then there are k to the power t possible sequences, which is really exponential, and it is not feasible to look at every sequence and find out the sequence with the highest probability. So we do an approximation which is computationally simple, which is at every state we keep k words. So if we have k words at the first time step, k words at the next time step, how many total probabilities are there? So how many total sequences are there of length 2? There are k words here and k words here. So there are k square sequences of length 2. Out of these k square sequences of length 2, we are going to choose the top k. So we have a beam size of k. If we did not have a beam size, if we looked at all the sequences, the total number of sequences will become k to the power t. And if we had considered all the words m, there would have been m to the power t sequences. So we restrict the beam size to k. At every step, we only output k possible words, and still then the total number of possible sequences is k to the power t. So what we are going to do at every state, we are going to only keep k. Out of the k square sequences we have found at time step 2, we will keep the top k. And then these top k will be composed with the k words at the third time step. And out of these k square, we'll again take k. So at every step, we carry forward k sequences. So Dipankar has a question, greedy decode repeat. So greedy decode means at every step, you take the most probable word. And in beam search with beam size k, you take the k most probable word. So in beam search, just to put it simply, at every step, if beam size is k, we look at k possibilities of sequences generated this far. So beam search may not give you the optimal solution, but it is still better than greedy method and more efficient than exhaustive search. So just to take an example, suppose in the decoder, in the first time step, you get the top two outputs as he and I. If you take he as the current word, then the next two possibilities are hit and struck. If you take I as the word, the next two probabilities, next two words with the highest probability are was and got. So you have four sequences: he hit, he struck, I was, I got. And for these four sequences, you are going to try to find their likelihood, find their score. Based on the score, you keep the two most promising ones. In this case, he hit and I was are more promising, so you prune the other two. So he hit. Based on that, you again expand to two words. You have and me. After I was, you generate two words, hit and struck. So you have again four sequences: he hit he hit me, I was hit, I was struck, and you compute their scores. You retain the two with the maximum scores. And after that, again, you generate for each one, you generate the next word. So you have two generated for this, two generated from this. So you get he hit a tart, he hit a pie, he hit me with, he hit me on. So out of these four, you are trying to find out the scores and choose the best. Now, how do you compute the score? You compute the score based on the probabilities of these sequences. And to compute the probabilities, we looked at the formula, which is this product. Now, this product can become very small. It is difficult to deal with such small numbers. So equivalently, we look at the sum of the log of these probabilities. So instead of looking at the product of the probabilities, we look at the sum of the log of these probabilities. Based on this, we choose these sequences. Is this okay? Any questions, anybody? So in summary, in beam search, we have this formula to find out the score of a sequence generated thus far by using the log probability, the sum of the log probabilities. And how does beam search proceed? At each time step t, for each hypothesis we have got in the previous time step. In the previous time step, we have k hypothesis. For each such hypothesis that you are tracking, you find the top k tokens at this step. And you get k square sequences of length t, and find out the total log probability of each of these k square sequences. Out of this, you keep the top k sequence, and then you proceed to time step t plus 1. Now, when do you stop decoding? When you get end of sentence. So there is a special marker at any path. When you get end of sentence as the output, you stop. Okay. So, different sentences that you are getting, different sequences will have different length. Now, after you have completed, after you have got k end of sequences, then you will find out the score of each of these sequences, and you will choose the sequence with the highest score. In this case, this is the sequence with the higher score. Okay. So Vinod has a question. If I have an image having some trees near a road, so to do machine translation, first I have to do semantic segmentation and give an input to the RNN, right? So Vinod, so we are not talking about what is captured by the CNN or what is captured by the encoder. We assume that information about the input is captured by a good encoder in a vector. So given an image, we assume that after your CNN, the vector that you got at the last time step captures all the semantic information about the image. Okay, this is the assumption. How it is going, whether it is capturing well or not, we just trust that the machine, once you have a lot of training data, it will learn to capture the relation well. We are not specifically trying to understand what objects and what relation it captures. Similarly, for natural language sentences, we are giving the sentence as the encoder, and we are giving a good encoder, which we hope that will be able to capture all information about the sentence in this vector. So Bharatram, do you have a question?
No, ma'am.
If you have a question, please put it in the chat. So in this sort of neural network, we are just treating it as a black box. We're not looking for explanation. We are just saying that we have a powerful encoder appropriate to the input type, and that encoder is coming up with a representation which is capturing all the relevant information of the input, based on which a decoder should be able to get the right output. Okay. So, and in the decoder, if we have multiple sequences, we find the score of the sequence by the log probability, and you take the sequence with the highest log probability. Now, you may find out that if a sentence is short, this value is likely larger because the log probability is a negative number. If a sentence is longer, it will become more and more negative. To compensate for this, sometimes to this score, you will have a multiplicative factor, which is 1 over the length of the sequence. So here you will take minus 3.2 by 3. Here you will take minus 4.5 by 6. 7, which is the length of the sequence. Here you will take minus 7.2 divided by 1, 2, 3, 4, 5, 6, 7, 8, 9. So you can normalize by the length of the sequence, and then you can choose that sequence whose score is highest. So in summary, in beam search, we compute the score by summing the log of the probabilities and normalizing it by dividing by the length of the sequence. At each time step small t, for each hypothesis that have been generated up to the previous time step. For that, we extend it by the top k tokens in the next time step. Out of these k square sequences, you keep the top k. So if any sequence ends in end of sentence, you terminate the sequence at that point. And you continue to the next step. When you have got k hypothesis ending in EOS, you stop, and based on this score, you pick the best sequence. So with this introduction about the encoder-decoder model, we will move on to the next topic, which is relevant, which is called attention. Now, attention is a very powerful context, a powerful concept, and it tries to address one of the problems with the encoder-decoder model. As we described in the encoder, we have a context vector, which is typically obtained from the last encoder state. And this fixed length context vector captures all information about the input. Right? And if the input sequence is long, then it is very difficult to understand that this can capture the input very well. Now, to get over this problem, what attention proposes is that we will save the hidden states at every time step in the encoder. So instead, suppose we have length-free sequence, we have H1, H2, H3 at the encoder. So in the basic encoder-decoder model, C equal to H3. But in attention model, we save H1, H2, H3. We save all these three hidden states. And then while generating the output at a particular time step, we may consider whichever of H1, H2, H3 or as many of H1, H2, H3 that is necessary. This is the concept of attention. So what we do is that, so from the hidden state in the encoder, we apply some function and get a key vector corresponding to each of these states. So this is key 1, key 2, key 3, corresponding to hidden time step 1, time step 2, time step 3 of the encoder sequence. Now, when we are at a particular state of the decoder, suppose we are at the Tth state of the decoder, we query from the Tth state, we generate the query vector of the Tth state, and based on the query vector, we find out which of these 3 states, or how much do we need each of these states in the encoder. For each encoder state, if there are n encoder states, we try to find out how much to take from each of the encoder states. That is obtained by looking at the similarity between the query vector and the corresponding key vector at each of the steps. So we have the query vector at time t of the decoder, and we have the key vector of time 1, time 2, time 3 of the decoder. So in general, suppose for the ith encoder state, we have ki. So based on the similarity of qt and ki, we decide how much importance we will give to the ith encoder state. We can use a similarity function such as dot product qt.ki, which tells me how much we should focus on the ith encoder state. Okay, and based on that, we are going to create a context vector which takes information from the ith encoder state. So in general, the context vector can look at each of the encoder state and sum them based on their importance. Okay, suppose I compute a score of alpha 1 for the 1th encoder state, alpha 2 for the 2th encoder state, alpha 3 for the 3th encoder state, where alpha 1 plus alpha 2 plus alpha 3 equal to 1. So we can take the context vector at time t equal to alpha 1 times h1 plus alpha 2 times h2 plus alpha 3 times h3. Is this clear to everybody? So in the RNN encoder, at every time step t, the key corresponding to the ht is computed by a function k of ht. Okay. The function k of ht, k computes the key value at the tth step of the encoder. So this is basically, this k is a neural network, a simple neural network having parameter values wk and bias bk. Now, from the ith state of the decoder, or let us say lth state of the decoder, we find the query vector of the lth state by using a function q over the SL is the lth state of the decoder. We use h1, h2, h3 for the encoder hidden states and s0, s1, s2, s3 for the decoder hidden states. So ql equal to q of SL. Q is also a function which can be a simple neural network having some parameters. Then we can find out the importance of the tth encoder state to the lth decoder state as ETL. And ETL is obtained by taking the similarity between QL and KT. And we can use any similarity function. The simplest similarity function is the dot product function. kt.ql, which does not have any parameter. You can also use a simple neural network to compute this similarity. Okay. Now, so this ETL will give me a score. So I will compute E1L, E2L, E3L, right? But these scores may not be normalized. So E1L, E2L, E3L, I will like to normalize them to get alpha 1L, alpha 2L, alpha 3L, so that they sum to 1. So we can use our favorite softmax function. So when we apply the softmax function to E1L, E2L, E3L, we get alpha 1L, alpha 2L, alpha 3L, so that they sum to 1. And then we can find out the context vector appropriate to the Lth hidden state CL. Here they are calling it AL. You can call it AL also, as summation over alpha TL over T. T varies from 1 to n, where n is the length of the encoder state. So alpha TL times HT. So I will pause here. So if you have any questions. So I am trying to compute the instead of taking a common context vector, which we obtain and giving it as in to all the decoder states, I am trying to find out decoder, step specific context vector. And the step specific context vector, I'm allowing the context vector to look at every state of the encoder. Instead of only keeping the last encoder state, we are storing in memory all the encoder states, right? And based on the current decoder, previous decoder state, at the current time step, we are trying to find out how much of each of the encoder states we will look at, right? That is, for this we obtain alpha 1L, alpha 2L, alpha 3L, where alpha TL, the importance to be given to the Tth encoder state. Then we find out the context vector at the Lth decoder state as alpha TL times HT, sum over all T. Is this okay? If you have any questions, please ask. So this is an example. So suppose we have a sequence of length 3. So we have this French sentence in reverse. And then we have got H1, H2, H3. And we have stored them in memory. And from H1, H2, H3, we apply our key function to get K1, K2, K3. Then this H3 appears as S0. And then I want to find out Q1 based on S0. So from Q1, I find out the similarity of Q1 with K1, K2, K3. And so I get E1, E2, E3. And E1, E2, E3 are scores of these 3 positions. We apply softmax to get normalized scores alpha 1, alpha 2, alpha 3. Okay. And based on that, I do sigma alpha t HT to get the context vector. And this context vector is used to produce the output. Now, after the first output has been produced, this output is fed to the next hidden state of the decoder. And from S1, we get Q2. The Q2, from Q2, we're using this dot product on K1, K2, K3, we get E1, E2, E3, normalized to get alpha 1, alpha 2, alpha 3. Again, we do this to get the context vector for this current state, and so on. Okay. So at every state of the decoder, we find a context vector specific to that state by being allowed to peek into different encoder state. This is the power of the attention model, which gets over the bottleneck problem, and it is able to try to identify which portion of the input sequence to focus on for the current output. So even if your input was a image, then the attention would focus on which portion of the image to focus on to generate the current word. Okay. So Vinod was asking about objects in an image. So without saying that whether the system has actually found the objects or not, so there are suppose there are multiple objects in an image. Suppose there's a bird on the tree, a bird sitting on the tree, or bird perching on the tree. So suppose bird is an object, a tree is an object. When you're trying to output the word bird, you would like to focus on that part of the image where the object bird is present, and that is possible by this attention mechanism. And if you're trying to generate translation, so when you're trying to generate it in the target language, you want to focus more on the phrase bird than the tree when you are trying to generate the corresponding output. So this is what attention lets us do. And thus attention is a very powerful concept. Are there any questions? So to summarize, these are the attention equations. We've already told. Then encoder side, we have KT is K of HT. Decoder side, we have QL equal to Q of SL. Then the score ETL is KT dot QL. Alpha TL is obtained by softmax from the ETL sequence. And then AL, the context vector for the LF decoder state, is obtained by this summation. And this context vector can be used to generate the next hidden state, and it also could be used to generate the output. Now, this key could, if you want a very simpler model, KT could be HT itself and QL could be SL itself. But we gave a more general model. You could also have KT as another function of HT that is useful when you have attention with multiple heads, which we will talk about later. But you could have KT is HT, QL equal to SL, or in general, you can have KT is some function of HT and QL as some function of SL. That is in general. But these functions could be identity functions also, as here. And therefore, as a simple dot product, you get this. And from this, you get alpha TL and AL. Yeah, of course, I will stop. I also have another class. So attention, as we said, we could use the identity matrix, or this KT could be a simple function based on this is multiplicative attention, where you have a matrix WK, and WK.HT will give you KT, and WK is the parameter that you wish to learn. So for the key, you have this parameter matrix WK. For QL, you have this WQ. So WK and WQ are two matrices that you will like to learn. Okay. So this is a second way of, so identity matrix and these are different attention matrices. Okay. So to summarize, attention, every encoder we produce a key KT, every decoder step we get query QL, and then from that we get these values and we use it for. So we will stop here today, and in the next class we will take over from here.